So, I got cut off because of the length of these screencasts, but the true value of statistical thermodynamics gets revealed when we take a partition function, such as this canonical partition function Q, and, sorry, don't have a pen, need a pen, I'll make it a color that stands out. We can take the partition function and derive a large number of macroscopic properties based on this partition function. So that's what really makes it useful. So to illustrate some of the other properties we can get. So I just talked about getting the average energy by taking the partial derivative of the log of Q with respect to 1 over temperature. If we look at some relationships from macroscopic classical thermodynamics, we can also say how to use the partition function for other properties. So for example, from macroscopic thermodynamics, we know that the average internal energy of the system is given by the partial derivative of the Helmholtz free energy over T with respect to 1 over T. And what that tells us, if we look at some of the definitions from the previous slides, is that the Helmholtz free energy is actually given by negative kT times the log of the partition function. So the partition function is directly related to free energy. And even though the partition function is kind of a abstract concept, free energies are kind of an abstract concept, at least we know how they're related to each other. And now with this in mind, we can then derive a wide variety of other properties. So the entropy, for example, is given by negative the partial of free energy with respect to temperature at constant number of particles and volume. Because of the relationship above, that means that we can derive this from the partition function. The pressure is the opposite of the partial of the Helmholtz free energy with respect to volume at fixed number of particles and temperature, and so that's kBT times the partial of the log of Q with respect to volume. The chemical potential can also be determined as the partial of the free energy with respect to the number of a particular type of molecule. So the way that statistical thermodynamics works is that we propose a set of interactions that will tell us the energy of the system. We derive the partition function, and then from that we can determine all other macroscopic quantities. So that's the way classical statistical thermodynamics works. It turns out not to be possible in all situations, in which case we need to use molecular dynamics and Monte Carlo simulations, but we're not interested in that. So I'm going to talk about two cases that give us some of the partition functions that are useful for transition state theory. One is a particle in a box, so an ideal monatomic gas. The first thing we need to keep in mind is that if we have n indistinguishable independent molecules, and each one of them has a partition function q, lowercase q, the total partition function of the system, capital Q, can be given by 1 over n factorial times q to the nth power. And this is assuming that each molecule is in a different state, which if there's a wide number of states, that's going to happen. Q is the partition function of a single molecule. The factor of 1 over n factorial is because the molecules are not distinguishable. So there's n factorial ways of arranging those molecules that are all the same. And then q to the nth power means that each one is independent, so each one has the same partition function. We just multiply them all together. To figure out what lowercase q is, we assume that this ideal monatomic gas can be treated as a particle in a 3D box, which from quantum mechanics, it can be shown that basically if we just assume that we have a box of a certain size and we solve the Schrodinger equation, the energy levels that we get for a box of size Lx, Ly, and Lz is given by this expression, which you can look up in a quantum mechanics book if you'd like to. It's Planck's constant squared times the sum of the squares of the lengths of the box in each direction over 8 times the mass of the particle times the L squared, so the total length squared. So that means that if we want to calculate Q, the partition function of the system, we take the sum for Lx, Ly, and Lz going from 1 to infinity. Oh, sorry, those are, I should be clearer. L is the length of the box, and Lx, Ly, and Lz are integers that define the state of the system. So the partition function will be given by the sum for Lx, Ly, and Lz going from 1 to infinity of the exponential of negative the energy associated with that state of the system over kT. And we can also write that as the integral from 0 to infinity of omega of epsilon, where omega represents the density of states, or the degeneracy of a particular state epsilon, times the exponential of the opposite of that energy over kT. And we integrate that. So to figure out what omega is, we take the density of states, and we can imagine calculating that by drawing a circle, or really a sphere in 3 dimensions, and counting the number of states inside of that circle. And then we can take the derivative of that. So the density of states with an energy less than a certain value epsilon is given by the number of states inside of a sphere of a certain size. So that density of states will be pi over 6 times 8me over h squared to the 3/2 power times L cubed, where L represents essentially the size of the sphere. And then we can find the number of states with an energy between epsilon and epsilon plus d epsilon by taking the derivative of phi, the density of states with respect to epsilon, and multiplying by d epsilon. So that's how we get omega that goes into this expression. Now all that I'm doing is saying how this is a convenient way to calculate the partition function. And it's what's basically used in classical statistical mechanics to do this. So to calculate lowercase q, so the partition function of one particle, we integrate this expression, and using what's on the previous slide, we can show that this is equal to the volume of the box divided by lambda cubed, where lambda is the de Broglie wavelength. It has units of length, and it's given by the square root of Planck's constant squared over 2 pi times the mass of the particle times Boltzmann's constant times the temperature. So it's a simple relationship. And then taking n particles, we can then calculate the total partition function of the system. So for a monatomic ideal gas where there are no interactions between particles, we get Q equal to 1 over n factorial, lambda to the 3n power times the volume of the system to the nth power. So for example, if we want to calculate the average pressure based on this partition function, it should be kBT times the partial derivative of the log of Q with respect to volume. And using this expression, this is what we get. We get n kBT times the partial derivative of the log of lowercase q with respect to volume, and that's n kBT over V. Now this may look familiar. If we replace the gas constant R with Boltzmann's constant Kb, this is exactly the ideal gas law. So basically by assuming that we have n particles, all of which behave independently, and we just put them together, we can derive the ideal gas law. Similarly, we can derive other functions such as the chemical potential of an ideal gas. That is given by this expression, which is from a couple of slides back, and we would get, based on the partition function, that this is the expression that we ought to have. And this is consistent with classical thermodynamics. So that's the idea of what we do with statistical mechanics. And this is the translational partition function. So it's just based on the relative positions of a bunch of particles in a 3-dimensional box. And this is going to be a component of the partition function of any molecular system. Now another system that can be solved analytically is an ideal monatomic crystal. And actually Albert Einstein derived this. So this is sometimes referred to, his name is associated with this. So the idea is that we take the potential energy of an atom in a crystal, and we assume that it's given by a ground state energy plus 1/2 of a force constant times the distance relative to the ideal position of that atom squared. So basically the atom acts like a spring. And if you move it outside of its ideal lattice position, it's as if we're stretching a spring. And because the particles are all going to be assumed to be independent, the partition function of the system is given by the exponential of the opposite of the ground state energy over twice kBT times the partition function of each particle raised to the 3nth power. Oh, and the first term is raised to the nth power. The energy levels for a harmonic potential, such as this one, can be found from quantum mechanics. It's one of the systems that's relatively straightforward to solve the Schrodinger equation. And you can show, and again, I'm just taking this from quantum mechanics, I'm not going to show it here, but the energy levels are given by these values. So integer n plus 1/2 times h nu, where nu is the frequency, and it's given by the square root of the force constant over the mass divided by 2 pi. So this is just a relationship from quantum mechanics, but it tells us the energy levels associated with the system. With that in mind, then, we can derive the partition function of one atom in an ideal monatomic crystal. That's given by the sum over all states of the exponential of the opposite of the energy over kT. And inserting the expression from the previous slide from quantum mechanics, we end up with this expression. So we have the exponential of the opposite of capital theta over 2t over 1 minus e to the negative theta over t, where theta is given by h nu over kb. So if we know the vibrational frequency associated with that particular state of the system, we can derive the partition function. So this is the entire partition function of a system of n atoms in a monatomic crystal. And for example, we can get quantities such as the Helmholtz free energy. It's negative kb times the log of q, and it's given by this expression. So for a system that has just a harmonic potential, this doesn't apply just to monatomic crystals, but this gives us the vibrational partition function of the system. So in the next set of slides, and I think this hopefully will be enough time to wrap up this set of screencasts, I'm going to talk about reactive systems and how we can use all the partition functions from statistical thermodynamics to derive a rate coefficient.